Chapter 11, Part 3, Synthesis and Reactions of Ethers. So first, let's take a look at some of the simpler syntheses of ethers. The first one is intermolecular dehydration of alcohols, which sounds a lot more complicated than it actually is. This is really just taking two alcohols and mixing them together in acid and heating it up. And so you're essentially doing like an SN1, SN2 style reaction here. So one possibility here is that you just end up dehydrating, right? And you end up with an alkene. The other possibility is that once you've protonated your hydroxyl group and it leaves and you have a carbocation, that the other equivalent of an alcohol comes in and attacks. This tends to happen at slightly lower temperatures where you don't favor elimination as much. Notice this is 180, this is 140, and this is being done with ethanol, and these are way above the boiling points of ethanol, so these are definitely done under pressure. In the case of a primary alcohol, you would end up protonating this, and then the alcohol comes in and attacks, and you do more of an SN2 situation. But that's one potential way that you can make an ether. So protonate, attack. Now you have your intermediate. You have two different equivalents of the alcohol. I'll go ahead and color code a little bit for you here. And then this would be from your other equivalent of alcohol. And then you just have to deprotonate, and then you have an ether. Now, this has a drawback that I hope is kind of obvious. With a symmetrical ether, this could work. This could be really straightforward. But if you need an asymmetric ether, you can have a mess. So let's say you want to mix together these two alcohols and you want an asymmetric ether. Sure, that's definitely possible, but you could also get two of the same alkyl group on there, and so you could end up making three different ethers. And that's possibly not what you're aiming for. Probably not what you're aiming for, to be honest. There is one exception though, is if you mix two alcohols together where one is highly substituted and one that is not, then you're going to end up with one product, because T-butyl ether is not going to be a good nucleophile. The best thing that it's going to be able to do is get protonated and then lose its hydroxyl group, creating a carbocation, which will make this automatically the nucleophile. And that could work pretty well. So that's one possible scenario there for making an asymmetric ether. But if you wanted to make like ethyl methyl ether, this would not be the way to do it. Here we go. So we're going to talk about the Williamson ether synthesis, which is something that you've actually done several times in SN2 reactions. You just didn't know that it had a name. Named reactions just basically happen when somebody creates something and then publishes about it. So it's an SN2 reaction, but it's also known as the Williamson ether synthesis. This is the best route to asymmetric ethers. It is an SN2 reaction. So in this situation, you take an alkoxide and you react it with something that has a good leaving group. So typically like an alkyl halide is the situation that you're talking about here. Usually an alkyl iodide, which would have the best leaving group. And that's just an SN2 reaction. So bromine, iodide, tosyl, mesyl, trifle, all very good leaving groups. This works best with primary or methyl electrophiles. So we're talking specifically about this portion. But also you do want to keep your nucleophile on the slimmer side. Remember, big nucleophiles tend to act as bases. If you do a tertiary substrate with the alkyl halide, then you're only going to see elimination. You're not going to see any substitution. So we're going to look at a practice problem here. So you can take a phenol, which is quite a lot more acidic than an alcohol, In this case, it's p-cresol or 4-methylphenol. And you can deprotonate this with hydroxide. And then you can react your alkoxide with an alkyl group featuring a good leaving group, such as the triple group, and you can make an asymmetric ether. So this is one situation where using those sulfonyl-based leaving groups can be really useful. So let's do a practice problem. Go ahead and pause and try to come up with the product for yourself. Okay, so we're reacting with 1-butanol, and our base is going to be sodium hydride. And the reason we're using sodium hydride is that the pKa of this proton is closer to 16, whereas the pKa of this proton is closer to like 9.5 to 10. And so this phenol proton can be deprotonated fully by hydroxide. Because remember, we want to fully liberate our nucleophile. We don't want to have half nucleophile and half conjugate acid still. But in this case, if we tried to deprotonate with hydroxide, we would be in equilibrium and we wouldn't have fully liberated our nucleophile. So reacting with sodium hydride puts us in a much better situation. Hydride is a stronger base than hydroxide, so we're able to fully deprotonate. So after step 1, the species that we would have would be 1-butoxide. And again, remember this is sodium plus and hydride minus. Hydride is a base. And then in step 2, you introduce your alkyl halide. And this is just an SN2 reaction at this point. You attack here, kick out bromine, and your final product in just one step here has all the carbons from your alkyl halide. And then in the place of the bromine, we're going to have our 1-butoxy group. So all 4 carbons here. So this is a really straightforward way of making an asymmetric ether. And it's just an SN2 reaction, and with a small update of you have to make your nucleophile first through deprotonation. You can also make ethers by alkoxymercuration demercuration. This is just an update on oxymercuration, and this is actually something that you've already seen. It was mentioned in your notes, and it was also in your homework. So this is just done by taking the conditions of oxymercuration. Notice here, this has a small update on the acetate using a trifluoroacetate, but it's not super necessary. You could still do this with a hydrogen there. And in the place of the water that would normally be here, you put in your alcohol of choice. And this is going to end up making an ether, and this is going to follow Markovnikov rules minus the potential for rearrangement. And this is a pretty high yielding reaction, so this is a good way to do this. And it definitely avoids the potential for side products. Even with the Williamson ether synthesis, if you combine the wrong things together, you have a chance of doing elimination. But in alkoxymercuration demercuration, you have a better chance of just ending up with the ether. 98% yield. It's pretty good. So there's another very specific type of reaction that is the making of a T-butyl ether by alkylation of the alcohol. And alkylation of the alcohol is kind of a strange phrase, and it's not all that different from doing something like a Williamson ether synthesis, where you're reacting an alkoxide with an alkyl halide or something that has a good leaving group. That's also alkylation of an alcohol. But T-butyl ethers are difficult to make by that route because T-butyl groups are not very good at being nucleophiles, and they're not very good at being electrophiles. They're not good for SN2 reactions. So instead, we use 2-methylpropene, and we react with an alcohol and acid. So I want you to pause and work on the mechanism for yourself for a second. If you need a hint, I'll give you one in just a second. If you want to pause and work without the hint, you can. Okay, if you're looking for a hint, think about what alkenes do in strong acids. This is the basis of electrophilic addition. What species do they form? Okay, let's work through this together. So the first step of this mechanism is the combination of the alkene and the acid. And sure, the alcohol could also get protonated, but the protonation of the alcohol doesn't lead us to anywhere in this mechanism, and the protonation of the alkene does. So that is the only protonation that we're going to draw. It doesn't mean that the protonation of the alcohol doesn't happen, it just means it's not part of the mechanism that gets us to our product. So we have our alkene, and we have our strong acid. I'm just going to write it as H+. The alkene picks up the proton, and we put the hydrogen on the least substituted carbon, and we create a carbocation on the most substituted carbon. So at this point, we've created a good electrophile. And if we were doing this in an electrophilic addition, we probably would have done this reaction with like hydrochloric acid, and then we would have some chloride floating around, and it would attack the carbocation. But in this case, we don't have some obvious nucleophile floating around. What we have is this alcohol. So the alcohol can come in and attack. And I'm going to stop drawing this hydrogen because it's implied. But now we have our oxygen from the alcohol, we have our R group, we have a hydrogen on there, we have a lone pair and a positive charge. So from here, we can just have another equivalent of the alcohol, pick up this proton, and that gets us to our product. So this is another example of the alcohol getting protonated here. Remember that when you put a strong acid into something like water, which alcohols are, they are going to have an equilibrium. And so you could actually imagine that, or not, you don't really have to imagine it because it is happening, but the alkene is picking up a proton from something equivalent to hydronium. It's just the protonated form of the alcohol. So that step does happen, and we could have drawn the deprotonation this way, but that just means that you have to draw another step in the mechanism when this is the part that I'm hoping that you understand. So this can be useful because you can actually use the T-butyl group kind of like a protecting group for alcohol. And protecting group is a term that's new to us. So we're going to talk about that on the next slide. So protecting groups are used in situations when you need a transformation to occur, but there's something else that interferes with that transformation. So for example, let's imagine that you had this alkynide anion and you wanted to take it and do an SN2 reaction, kicking out the bromide. It's a little problematic because you're going to end up with a different reaction instead. This is a strong base. This is an acidic proton. What's going to happen instead is your base is going to come and pull off that proton. And that is not really what you want, because then you end up with an alkoxide, and you might end up with cyclization. That would make a small cyclic structure in this case. That's not totally favorable, but at this point, you've quenched your nucleophile. You've totally killed it off by protonating it. So what we can do instead is protect the alcohol. We can take our original compound and do the reaction that we just looked at and alkylate the alcohol with a T-butyl group, and this gives us a T-butyl ether. Now, when we introduce our alkynide anion, which I know has been on the screen for a while, that was a whoopsie in animation, I guess, we can kick out the bromine, and it's not going to be interested in the alcohol because there's no longer a proton to get in the way. And this gives us kind of on the way to our compound, we still have this T-butyl group. We can deprotect the alcohol by adding in aqueous acid, because what's going to end up happening is you protonate this and it's going to get replaced with water. And now you have your intended compound, and also an equivalent of T-butanol. Now, there are other protecting groups that may or may not be easier. These are definitely ones that tend to trip up students, because we already learned about tosyl, tryptyl, mesyl, which are leaving groups, and now we're going to learn some protecting groups that have kind of similar sounding names. This is the tert-butyl dimethyl silyl ether protecting group, which is often shorthanded as TBS. And to make this, or to use this rather, you take an alcohol and you react it with TBS chloride. So this is often shorthanded like that, just like tosyl chloride, tryptyl chloride, so forth. Imidazole is very similar to pyridine. It is also an aromatic heterocycle and is used as a base to deprotonate the alcohol after that initial attack on the silicone atom. Once you're done using the TBS protecting group and you need your alcohol back, you do that by adding in fluoride ion. And the best way to add in fluoride ion is to add in something that's also not going to interfere with your reaction. So this is tetrabutyl ammonium fluoride. And so this is often shorthanded as TBAF, which is delightful, I guess. So TBAF is tetrabutyl ammonium fluoride. It's just a source of fluoride ion, and that's going to attack the silicone and kick out your alcohol here. So you can get your alcohol back and you remove TBS fluoride. So very similar to TBS chloride. So let's look at reactions of ethers. Ethers are not particularly reactive in most situations. That's why they're often used as solvents in organic reactions. But if you add in acid, you can protonate them, which would make an oxonium salt. You can also cleave an ether, break it apart, by reacting with an excess of a halogen acid. So what ends up happening is you protonate one equivalent, or like one side of your ether, basically, and then the bromide attacks and kicks it out, and then the resulting alcohol from this side of the reaction gets protonated and reacts with bromide again. So just continuous SN2 reactions, or if your ethers are highly substituted on the sp3 carbon attached to the oxygen, it would work through an SN1 mechanism. This actually works pretty well with an alkyl aryl ether, so an ether made from a phenol derivative, so something like this. And the reason this works so well is that your alkyl halide can leave, and you leave behind phenol, and you don't have to worry about phenol reacting and being replaced with a halogen. So this is one way also that you could actually protect a phenol and then get it back by reacting an acid.